Have you ever wondered how integral calculus is applied in various fields? Well, you're about to find out. Integral calculus, a branch of mathematics, is a fascinating subject with a world of applications. At its core, it's about finding the total when we know the rate of change. Think of it as a means to calculate the whole from a series of parts. It's like piecing together a puzzle. Now, you might have heard about the relationship between integrals and areas under curves. This is because one of the most common applications of integral calculus is to precisely calculate areas, volumes, and other quantities that can be defined as the total sum of many small parts. It's an essential tool in physics, engineering, economics, and even in the realm of computer science. Now that we have a basic understanding of what integrals are, let's dive into the different types. In the world of integrals, two kinds reign supreme: definite and indefinite integrals. Both are essential tools in calculus, but they serve different purposes and are calculated in distinct ways. Let's start with indefinite integrals. These are integrals without defined limits, and they represent a class of functions. When you calculate an indefinite integral, you're essentially finding a family of functions that could be the antiderivative of the original function. On the other hand, definite integrals have specific upper and lower limits. They are used to calculate a precise quantity, often representing the area under a curve or the total change over an interval. When you calculate a definite integral, you're summing up an infinite number of infinitesimally small quantities over a particular interval. So in a nutshell, indefinite integrals give us a general formula, while definite integrals deliver a specific value. With this knowledge, we can now explore the various methods used to calculate these integrals. Integration isn't a one-size-fits-all process. There are different methods for different scenarios. Let's start with integration by parts. This method is like the reverse of the product rule from differentiation. It's particularly useful when dealing with an integral that's a product of two functions, where one function integrates easily and the other one differentiates easily. The formula for integration by parts is derived from the product rule of differentiation and might remind some of you of a catchy little jingle: u times v minus the integral of v do. Next, we have trigonometric substitution. This method is based on substituting a trigonometric function for a variable to simplify the integral. This can be especially handy when dealing with integrals involving square roots of quadratic expressions. For example, a square root of a sum of squares could be simplified by using a sine or cosine substitution. Then there's the method of partial fraction decomposition. This method is used when integrating rational functions, which are functions that can be written as the division of two polynomials. The idea here is to break down the complicated fraction into simpler fractions which are easier to integrate. The process is a bit like unbaking a cake. You're trying to figure out the ingredients that went into making the original function. And let's not forget the straightforward method of substitution, often the first method taught in calculus. It's like a game of substitution, where we swap a more complicated expression with a simpler one, making the integral easier to solve. These methods, integration by parts, trigonometric substitution, partial fraction decomposition, and substitution, are the workhorses of integration. They each have their strengths and are best suited to different types of problems. Now that we know how to calculate integrals, let's see how we can use them in real-world applications. Integral calculus isn't just a mathematical concept, it's a tool used in many fields. Let's dive in and explore its diverse applications. First off, we have geometry. Here, integral calculus is a fundamental tool used to calculate areas under curves and volumes of solids. For instance, if you want to determine the area bounded by a curve and the x-axis, you'd use definite integrals. Similarly, to find the volume of a solid of revolution, you'd use the method of disks or washers, both of which involve integrals. But it's not just about shapes and spaces. Integral calculus also plays a vital role in physics. It helps analyze mechanical and electrical systems and model physical phenomena. For instance, in mechanics, integrals are used in finding the center of mass and moment of inertia of an object. In electricity and magnetism, the electric field created by a charged line or the magnetic field generated by a current-carrying wire are calculated using integrals. Now let's take a step into the world of probability and statistics. Ever wondered how probabilities are determined? Well, integrals are at the heart of it. They're used to calculate the probability of an event by integrating the probability density function over the desired range. They also come in handy when it comes to statistical data analysis, especially in deriving expectations and variances of random variables. Next up, we have the theory of differential equations. These equations describe dynamic systems that change over time. Think of a population growing over time or a ball falling under gravity. In such cases, differential equations come into play and integrals are a crucial part of their solution. They help us understand the behavior of these systems over time. Integral calculus isn't confined to the physical world, it has found a place in the digital world as well. In computer science, integral calculus is used in algorithm analysis. For instance, it's used in determining the time complexity of algorithms. Imagine you've written a piece of code. You'd want to know how long it will take to run, right? That's where integral calculus comes into play. Furthermore, integral calculus is integral to the field of engineering. Whether it's civil, mechanical, or electrical engineering, you'll find integrals at work. They're used to model and solve problems related to heat transfer, fluid flow, stress and strain in materials, and much more. For example, in civil engineering, integrals are used in the analysis of structures like beams and columns, while in electrical engineering, they're used in the analysis of circuits. As you can see, integral calculus is more than just an abstract mathematical concept. It's a practical tool with wide-ranging applications. It helps us understand and navigate the world around us, be it through calculating the area of a field, predicting the behavior of a dynamic system, analyzing a piece of code, or designing a bridge. But with all its applications, integral calculus can also present some challenges. Integral calculus, while powerful, isn't always straightforward. Sure, it's a potent tool in our mathematical arsenal, but it has its fair share of complexities. For example, dealing with improper integrals, those with infinite limits or discontinuous integrands, is not as simple as our basic techniques allow. These require a more nuanced approach, often involving limits. Then there's the world of multiple integrals. When we step into two or more dimensions, things get a bit more intricate. Double, triple line surface volume integrals, each with their own methods and applications, add layers of complexity to integral calculus. And let's not forget about the theory of special functions. These are the functions that arise in mathematical physics and other disciplines, often defined by integrals themselves. They can be tricky to handle, but they open doors to a wide range of problems that can be solved analytically. Despite these challenges, we have found ways to approximate integrals. The journey of understanding continues. When an integral can't be solved analytically, we turn to numerical methods. Now, what does this imply? Well, in some scenarios, an integral might be too complex or even impossible to solve by hand. In these cases, we use numerical methods which provide approximations to the exact value of the integral. Two widely used numerical integration methods are the trapezoidal rule and Simpson's rule. The trapezoidal rule, as the name suggests, approximates the area under the curve as a series of trapezoids. On the other hand, Simpson's rule uses parabolas to estimate this area, often yielding a more accurate result. These methods are not just mathematical curiosities, they are crucial in solving practical problems. For instance, in physics and engineering, numerical integration is used to simulate systems that can't be solved analytically. In computer science, it's used in algorithms to solve complex computational problems. And with that, we've explored the diverse applications and methods of integral calculus. Keep in mind that this is just the tip of the iceberg. There's so much more to learn and discover.